Okay.
Fine. So anyway, so okay. Good morning, everyone. It's a pleasure to welcome back Tong Zhang.
Yeah.
I say back because he was a student of Sebastian Bergeret and myself here. So he graduated in 2022, right?
Yeah.
And so it's been 3 years away.
No,
but-
2020.
It's 2020.
Oh, sorry, 2020 was.
Yeah.
Okay. Looking old. And yeah, during those 5 years that you were away, he was in Hong Kong for a while, right?
Yeah.
And then, okay, well, before then, he was also in Basel during the pandemic. And then he moved back to China and stayed in Hong Kong for some time. And then eventually made his way to the institution where he is now associate professor in Beijing at Beijing Institute of Technology. And today, actually, he's going to tell us about some nice results that he got, actually revisiting something that he worked during his PhD, right? This theory of magnetoresistance in ferromagnets, and also some extension to altermagnets. Okay, so whenever you want, thank you very much for being here.
Okay. Thank you. Thank you. Thank you, Professor Clotilde, for introduction. Also for your invitation. It is my pleasure to come back to PC. As I was the PhD students of both Professor Clotilde, also Professor Sebastian Bergeret. Yeah. Today I will talk about the micro theory and the applications of the magnetoresistance effect in Mesoscopic, ferromagnetic, and altermagnetic. Yeah, we know finite is always complicated. Here we focus on Mesoscopic setup. So finite is always complicated because we know the translation symmetry is broken. Also, we have to include the interfacial effect. So, but finite is always useful. This we know as the setup becomes smaller and smaller, especially the more low fares. Yeah. Thank you.
Maybe you can talk a little bit louder.
Okay.
Can you talk a little bit louder?
Okay, loud. Okay. So yeah, maybe I should use it. Oh no.
Yeah, it works. Yeah.
It works.
Yeah.
Okay. So this is my outline. Yeah. In the first part, I will present our micro theory developed for the spin-Home resistance in this normal heavy metal magnetic insulated heterostructure. Also, I will show our experimental demonstration of the spin-Home resistance in both ferromagnetic insulator GGG and ferromagnetic insulator European sofa case. This part was done when I was a PhD student and supervised by Sebastian. Yeah, and in the second part I will present our recent work about the microscopic theory of the magnetoresistance in the mesoscopic, the ferromagnetic and altermagnetic material and its application. So we know one of the most important application of the Spintronics is the volatile memory technology. Here, in each memory sphere consists of a ferromagnetic, normal metal ferromagnetic heterostructure. Then the giant magnetoresistance effect tells us there is two states, the low resistance state and high resistance state correspond to parallel and anti-parallel orientation of magnetization. This corresponds to logic 0 and 1 state. So the natural question, also the one basic question, is how to manipulate the resistance state. Yeah, the first one is the spin injection. So we can generate spin by inject a charge current into a ferromagnetic, then you will generate spin current. So this case corresponds to the spin transfer torque, to achieve spin transfer torque. However, there is a obvious disadvantage is that because the charge current will pass through this memory, so suffer from the heating problem. So then to solve this problem, then someone proposed another mechanism they call the spin Hall effect. So we can generate the spin Hall current in a non-magnetic conductor. Then this is correspond to the, then in this case the charge current is in this direction. Only the neutral spin current will go through the memory. So this ferromagnet. Here we will focus on the later. Then here we give an intuitive explanation of the spin Hall effect. Yeah, here we consider whole bar device made up of, for example, non-magnetic. For example, is platinum. It has a strong spin coupling. When we inject a charge current, then the spin up electron will deflect to the right, while the spin down electron will deflect to the left. As a result, we will obtain a pure spin current in transverse direction. So then, the right figure here, we show the inverse spin Hall effect. When we inject a pure spin current, then we will obtain charge current in transverse direction. So Valenzuela et al. They observe this spin Hall effect directly in their experiments. So they inject a spin current from a ferromagnetic insulator into a non-magnetic conductor. Then the inverse spin Hall effect convert this spin current into charge current. Then we will obtain the non-local voltage. Yeah. Now we already introduced the spin Hall effect. Now, if we consider setup with the spin Hall effect, then we find that the charge current in this setup, it will always contain two contributions. The first one is the uniform contribution. It includes the collection of the spin Hall effect and inverse spin Hall effect. The second part is the diffusive one, very interesting, where the inverse spin Hall effect is parameterized by this theta sh and a. Here a is x, y, z in three directions. So you will convert the diffusive charge current into the diffusive spin current into the charge current. So if we consider the uniform infinity size, then only the uniform current survive. However, we know the spin Hall effect, spin Hall angle is almost independent of the magnetic field. So it's really hard to tune the charge current by tune the theta sh. Now, next we can consider the finite size effect. For example, we consider with a finite size system with a thickness dm, then we can always integrate over thickness direction. Then we obtain the longitude. Here we assume our setup is uniform in xy plane and the electric field is in x direction. In this case, we can directly from this to here, we can find the longitudinal resistance is only depends on h spin y. This is from here to here. So the question then, all the story is about how to tune this h spin accumulation by the magnetic field, the resistance phase. Yeah. Then the simplest one is that we call it handle precision, which means the spin will rotate it along the direction of the external magnetic field. So here, mu s is the spin polarization of the spin Hall current. So then for example, if we rotated along x and y and z direction, which correspond to perpendicular to the spin polarization of the spin Hall current. Spin Hall current is always in y direction in this setup. Then we find the h spin y will change. This is why we will obtain the resistance will oscillate with all this angle. Then we consider another case if the magnetic field is rotated along y direction, which is parallel to the spin polarization. Then the y component will not change. This is why we obtain constant. Then another way is the spin Hall magnetic resistance. Then if we put the normal metal on a top of a ferromagnetic insulator, then the H spin mu s, for example, mu s0, it will be modulated by the spin-dependent scattering, which is happening at the interface, at the magnetic moment at the interface. So we know here we consider two cases for when the spin magnetization is parallel to the spin polarization of the spin Hall effect. In this case, the spin will accumulate in this at H. Then it will generate, there's so many spin accumulate here, it will generate diffusive spin current, which has different direction to drive the spin Hall current. Then this spin current can come back to the charge current by inverted spin Hall effect. This charge current has the same direction. Its JC plus has the same direction of JC. This is why we obtain the low resistance state. Now, if we consider another case, the magnetization is perpendicular to the spin polarization S. In this case, the spin polarization of normal metal will be fully absorbed. So there's no diffusive spin current come back to the charge current. Then we obtain the high resistance state. So with these two pictures, we can explain the magnetic resistance, spin Hall magnetic resistance effect in platinum big heterostructure. Here, the magnetization is fully controlled by the external magnetic field B. So when we rotated along x and y, s and z direction, which is perpendicular to the spin polarization of the spin Hall current, then we obtain this oscillate behavior. If we magnetic field rotate along the y direction correspond to parallel to the spin polarization, then it's a constant. So this is the two-way we give a qualitatively explanation of the spin Hall magnetic resistance and the handy magnetic resistance. Here, then the first spin Hall magnetic resistance is given by Chen et al. So they introduced a phenomenological parameter called the spin missing conductance, G up down is equal to GR plus IGR, to describe the boundary condition at the magnetic interface. Here, the JS and the mu s is the spin vector, and the m is the direction of the magnetization, which is controlled by the external magnetic field. Here we assume. So the first term, GI, the real part, it corresponds spin transfer torque. The second part is the field-like torque. Here, because this is only the phenomenological parameter, so they are assumed to be independent of the magnetic field and temperature. Yeah, though this theory has established and have given a qualitative description of this spin Hall magnetic resistance. However, here, because all this spin missing conductance is constant with temperature. However, there's so many experiments, they already observed the spin Hall magnetic resistance should be depends on both temperature and also the magnetic field. So especially also the magnetic configuration of the of this ferromagnetic insulator also play an important role. Then to understanding all these experiments, then we work together with Sebastian, also Italy. We developed a microscopic theory of the spin Hall resistance in this heterostructure. Here is our physical model. Here, for example, the normal metal have the connected term, also the Zeeman term, also the spin of the coupling. While, also the local moment is described by the Heisenberg model. For example, here is also Zeeman term. Here, the Gm equal to 0 correspond to paramagnetic insulator. For positive Gm correspond to ferromagnetic insulator. Of course, our model can be generated with any other magnetic insulator. For example, can be anti-ferromagnetic or ferromagnetic insulator. Then here, this is our setup. So here we already shown that if we inject charge current, you will generate spin current in transverse direction. Though the spin cannot float into the magnetic insulator, but it will be scalar. It will be scalared by the local moment at the interface. Then to model these scalar events, we assume a virtual layer between the normal metal and the insulator, where the local moment under the electron, free electron, coexist. They are coupled by this, we call it SD coupling. Is the spin exchange between free electron and the local moment. Here, positive JSD corresponds to ferromagnetic SD coupling. Negative JSD corresponds to anti-ferromagnetic SD coupling. Now, then we can go back. So we know the key to the magnetic system is the spin exchange. Here can be right to this term. Then, for example, if we begin with the local spin is up, then free electron is down, then the spin exchange will transfer the spin polarization from the free electron to the local moment. So we can use the spin polarization in free electron generated by spin Hall effect as we introduced, then to achieve the flip of the magnetization, which means then we can achieve to the writing of the memory. Notable, we find that the spin exchange is always accompanied with the quantum decoherence, especially the quantum spin decoherence. The quantum coherence is at the heart of the quantum mechanics, especially when the particle is a superposition state. So it can be always quantified by the off-diagonal density matrix like this. For here, we can consider the superposition of the spin plate. So it's up and down. So from here, we can clearly have the quantum decoherence have two contributions. The first, we call it the dephasing. Here, which means that this is generated by some scattering, which randomize the relative phase between these two superposition states. So this is parameterized by T5. Another one is we call it relaxation, because it also depends on the amplitude of this superposition. So the decay of the amplitude, it will also contribute to quantum decoherence. So the total one is we have to combine this dephasing and relaxation contribution. Then we obtain the conventional relation of the spin decoherence, which contain the relaxation contribution and the dephasing contribution. Here, the relaxation contribution is corresponds to the typical T1. Then the quantum decoherence here, T perpendicular is the correspond to the T2, conventional T2. Now, then before is some qualitative description. Now, when derive this analytically, here we use the open quantum theory. Then based on the quantum theory, then we derive the longitudinal and transverse spin realization time. Is top parallel and top perpendicular. We find it will depend on the interfacial parameter. For example, the impurity, the density of the local moment at the interface, also the SD coupling, the quantum coupling theorem. Also, it will depend on the spin excitation, also spin-spin correlation, which we know is depends on the temperature and the strength of the magnetic field. So then because of the previous theory, they assume they are, especially for example, the spin missing conductance is a phenomenological parameter. There is no any temperature and magnetic field dependence. Now, but here we throw based on quantum open quantum theory, we include this temperature and the magnetic field dependence. Then to connect to the previous theory, we rewrite the boundary condition, which means the spin current at the magnetic interface with the same form with the previous theory. In addition to the spin missing conductance, these two terms, we also obtain the spin sink conductance. It's directly proportional to the inverse of the spin realization time, longitudinal spin realization time. We know this longitudinal spin realization time is relative to the spin flip process. So it will be always connect with the magnum emission in observation. While the real and the imaginary part of the spin missing conductance describe the anisotropic spin realization and the interfacial exchange field. So now all these spin-related conductance, they are not phenomenological parameter again. They are related to all this microscopic model. They are related. They can be determined by all this spin realization time, also the spin exchange field. So that will depend on the temperature. Yeah, this is the main result of the first one. Also, then we consider for example, then we consider for the ferromagnetic case. For example, here the GR minus half GS and the minus half GS correspond to interfacial exchange field and the spin dephasing and the spin flip processes, which means spin realization. Then the right figure plot the ferromagnetic case. Clearly, we find, for example, the interfacial exchange field will be vanishing after T larger than Tc. Then this is some qualitative description. Now we give some qualitative. This is quantitatively. Then we give some qualitative description. Now we consider two regimes. One is called isolated regime. Here it happens for low field and a high temperature. In this case, we reach the spin of the magnetic insulator. They will also randomly. So in this case, we become isotropic case. Then we obtain spin missing conductance is 0, while the spin single conductance is finite, because the spin flip is really easy to happen in this case. Then if we consider the high field and the low temperature regime, then the spin of the local moment will align along the direction of the magnetic field. In this case, we reach the anisotropic regime. Then we have finite spin missing conductance and the 0 spin sink conductance, because the spin flip is suppressed. We cannot flip the spin anymore. Then with our derived boundary condition, where all these spin correlated conductance is not constant with magnetic field or temperature, then we substitute this boundary condition into the spin diffusion equation. Then we obtain the physical quantity, measurable quantity. For example, the longitudinal and transverse resistivity. Here, the dead row 1 and dead row 2 are really important quantities, which is experiment we can measure it. For example, the dead row 1 corresponds to the amplitude of the oscillation. Here, dead row 1 and dead row 2, they are depends on all these spin related conductance. So we know this spin missing conductance, for example, they depends on the spin expectation, also the spin correlation. So they are not the phenological anymore. We obtain the microscopic expression, also the mechanism of this. That's also especially all this temperature and the magnetic dependence also include the magnetic state of the magnetic insulator. For example, for antiferromagnetic, the temperature dependence or field dependence will be different. So in conclusion, then we find the magnetoresistance is relative to the electron to spin decoherence, which include the relaxation and dephasing. They are strongly rely on the temperature and the magnetic field, also the magnetic configuration, also the relative orientation of the magnetization. Then this is the main result of I work with Sebastian also Italy. Then this is purely theory. Now we want to show the experiment demonstration. In the experiments, we consider two cases. The first is the paramagnetic GGG and the ferromagnetic insulator European so far. So let's begin with first case. So the left figure plots the delta rho 1 and delta 2 as a function of a magnetic field. Here, the dot is experiment data. The line is our fitting, our theory fitting. You will find their fit where. Here, during fitting, because we mainly tuning the density of the local moment under the JSD coupling. And the other parameter, because we always have so many parameters in our model, so it's mainly given by experiment. Here we want to tune these two parameters, then we obtain this fitting. Yeah. Then we find the ratio between the real and imaginary part of the spin missing conductance is around 1, totally different from the previous ferromagnet case, which is much larger. So which means the field like torque is as important as the spin transfer torque. And then we also fit in the temperature dependence of the ferromagnetic insulator European so far. Then here, though the fitting is not as perfect as the paramagnetic case because we fit in the temperature. It's really hard to achieve perfect fitting in all this whole temperature regime. Here we find the ratio of the real and imaginary part can be smaller than 1, which means the field like torque can be much important than the spin transfer torque. Okay, then before is the previous work when I was in PhD here in the PC. Now then we focus on the interfacial spin exchange happen at the interface. Then the spin relaxation, spin decoherence, spin exchange is included in boundary condition by these spin missing conductance. Next we go to the bulk spin exchange. So here we include this spin flip or spin decoherence process by inside the spin diffusion equation by this spin relaxation length, which means spin relaxation time. But in boundary condition, we set is equal to 0. And spin current is equal to 0. So first, let me introduce our theory in ferromagnetic magnetoresistance in a ferromagnetic. As we introduced in the introduction, we know the longitudinal resistance charge current will depends on the H spin Y component. We know this is H spin. However, the previous theory, they only focus on for example, the anisotropic spin relaxation type. They only focus on the Joule conductivity. They said because Joule conductivity is relative to the momentum relaxation time. Here, we totally change because you related the spin, H spin. So we transfer from momentum to the spin relaxation. Especially, we already know this spin relaxation is really strongly depends on magnetic field and the temperature, also the magnetic state. I think this is then this is our setup. We consider, for example, inject a charge current in expression. Then you will the spin orbital coupling will generate a spin current in transverse direction. Then because we have here is a ferromagnet, so the spin current will be decayed. Spin will absorbed by the local moment during the propagation inside the setup. Then you will cause some spin accumulation on the edge. Then you will return back to charge current by inverted spin coefficient. So then I solve the spin diffusion equation also with boundary condition where the spin diffusion time, spin realization time depends on temperature and magnetic field. We all obtain the longitudinal resistance is given by this one. This is so compact because before this the experiment, also the previous theory already obtained this more or less this expression, but they are always purely phenological. Here we for the first time we obtain this compact expression. For example, here the dead row one is on the dead row. Sorry, the dead row one is even relative to the angular dependence. Then you throw the depends on the dead row one is depends on the longitudinal spin realization length. While dead zero is longitudinal realization. Dead row one, it will depends on both the longitude one and also the lambda. Lambda is depends on the transverse spin realization and the highly precision. So this term. Then through the spin realization, we introduce all this temperature and magnetic field dependence. So this is the result because the previous I discussed with some experiments, also the theory in the magnetoresistance. Who are working on the theory of the magnetoresistance, they are so surprised that we have obtained such a compact and clearly.
Sorry,
yeah.
These are the same expression you have in the previous part.
Yeah, this is the same. Yeah, totally. Because
and the other part is also if you wish, microscopic.
Yeah. So but here the difference is that we include the spin realization time. Yeah. I think also we did, yeah, this is I suggest you suggest me to do like this one. Also, you also asked me to include spin realization both in the magnetic insulator, also inside the LED. Yeah. So here I only focus on the bulk system. So because I was so surprised, the previous community, the previous magnetoresistance, they only observe all this but they never can explain how to cause this angular, for example, this angular dependence. Here, we give a really compact expression.
But you need a ferromagnet and spin hole.
Yeah, we need ferromagnet. In this case, we need ferromagnet and spin hole. Yeah, but it's always the case the magnetoresistance they require both the spin orbital coupling and the ferromagnet. I mean the spin exchange. This is just generalize the previous result just from the interfacial to the bulk spin exchange. Yeah, this is there. I think I divide this. The experiment really like this theory because it's so compact. The previous is always phenological one. Then we have with this expression. Let me explain the physics behind this. So here. The first term, the dead row term, as we say, is relative to the longitudinal spin realization time spin diffusion length. So it's caused by the magnum emission and observation. So for example, when T is equal to Tc, which means the spin is randomly with the vanishing magnetization. In this case, the spin polarization generated by spin Hall effect will be observed by this randomly local moment. This is why we call the first one is the magnum magnetoresistance. Also, the second one is dead row one. It will depends on the longitudinal spin diffusion length. Also, we call it the spin missing length here. Is to compare to the spin missing conductance. So it will depends on the transverse spin realization time and the highly precision. then this term will contribute anisotropic magnetic resistance. For example, we consider two cases. First, we artificially remove the Henry precession. In this case, if the system have spin anisotropic, which L parallel is not equal to L perpendicular, then this dead row one is non-zero. Then we obtain this oscillation behavior. Then, for example, if as the spin polarization is parallel to the magnetization, in this case, they cannot be observed. The local moment cannot it is not able to observe the spin polarization. In this case, we will obtain the low resistance state. Also, if the spin polarization is perpendicular to the magnetization direction, then the spin polarization generated by spin Hall effect will be absorbed by the magnetization. Then you will be high resistance state because the H spin Y will become smaller. Now, another case is that we can artificially set the spin realization is finite, but keep the Henry precession. In this case, we will also obtain the non-zero dead row one. Then we obtain the Henry magnetic resistance. For example, if the magnetic field is parallel to the x direction, so here is x direction, then the Henry will process the spin, will rotate it along the magnetic direction. Then the H spin Y will become smaller. Then we reach high magnetic resistance state. Another case, we pair magnetic field in Z direction. In the same case, you will rotate it like this way. Then the H spin will also reduce. This is why we obtain high resistance state. So what we do is really simple. We just introduce the spin realization type in diffusion equation. Then we obtain all these microscopic expression, all the physical picture. Then also we have found some application. So we know the longitudinal resistance is a proportion to the quadratic function of Bx minus B spin exchange field. So the minimum will be happen when external magnetic field is equal to spin exchange field. So we know the spin exchange field is proportional to the JSD, which means we can from the minimum of the longitudinal resistance, we can read out the spin exchange field. This proposes a simple way to detect the spin exchange. Also, we know the spin exchange field will depend on temperature. So somehow we can mimic the minimal behavior, temperature dependence, like the Kondo effect. Okay, then we go to the altermagnetic case.
Just before that, but
Yeah.
then you need, I don't know what it's ferromagnet, but your ferromagnet is a kind of alloy magnet dilute, because these two fields should be of the same order, no? And BSD might be huge in a real ferromagnet, no? If you take cobalt, then you need to apply a field, I don't know, which is...
I totally agree with you. Yes, sometimes so here we prefer some, it's not so strong. For example, the JSD is not so strong. Otherwise, here it will reach to 100.
Or close to the grid temperature.
Okay, yeah, but the 1000 Kelvin, then.
Yeah.
Well, it depends on what is
the cobalt, no?
No, I can
Not yet, but for other materials.
Okay, iron, 300,
okay. So here we have to choose really, here the spin exchange field is not so high, because if it's for example, effectively in some material, it can be 100 Tesla. But here,
and I think you assume, again, impurities, kind of, no?
But in this term is fine, because this is the effective spin exchange field. So it's only proportional to the density of the local moment. So it can be uniform or it can be non uniform. But if the first order, this is the first order effect. So I would say it's fine.
Yeah, but then, okay, good, fine. But then in your model, you have your spin orbit, you separate it from that exchange. So you have terms which are, and in the diffusion equation, there will be terms probably mixing them, and I don't know, new terms. Did you explore that?
No. We treat separate.
Yeah, which I think what is the main, okay, good. This I think there will be the
Yeah, because this is the reason why, because I try to explain the experiments into the magnetoresistance community. It seems this community they focus on experiments. They didn't go deep inside like our case. So this is why I just give some simple physical, then we obtain something interesting for them.
Fine.
Yeah.
Okay.
Then we go to the altermagnetic case. Here, then we consider the interplay of two ways of the spin generation. For example, the spin Hall effect and the anisotropic spin split effect. And then here the spin Hall effect is induced purely extrinsic so the base structure is still quadratic. It's only caused by skew scattering. Then we consider for the spin split, we consider for example, here we consider spin split effect, which is they have the orientation angle called theta. Theta here is the pi over 4. Yeah, around. Of course, our theory can be achieved for arbitrary theta or arbitrary orientation. So now, following the previous way, we develop in ferromagnet insulator. Then we derive the longitude resistance. Then we find in addition to this term, we obtain a cross term, which is caused by the interplay of the spin Hall effect and spin split effect. This term will surprisingly linear to the near vector. This is because of the cross term, the interaction between these two. Also, different from the previous case, here is a near vector. It's not a magnetization anymore. So now let's try to. Of course, I didn't show how to derive this because it's just following our previous way. I think even is simpler than our spin Hall magnetic resistance. Yeah, but here I just show the result. Now let's go to let's show the first term, which is proportional dead rho 1, is because we obtain this angle, we call it anti-ferromagnetic anisotropic magnetic resistance. So here is the magnetic resistance as a function of the near vector rather than the magnetization. In the previous anisotropic spin magnetic resistance is related to the magnetization direction. So here we use near vector. So this is the different. Another way is that we obtain this additional term proportional to spin Hall effect angle and the spin split angle. Then we find more complicated anisotropic magnetic resistance effect because this linear to near vector term. So this can be because this is only happen for the spin altermagnetic when we have anisotropic spin split. So it can be a factor of the altermagnet. Now, then we show our application. We said here, we emphasize, we use this linear term to achieve the electric result of the near vector because the ny, this term depends on ny. For example, for ny is equal to plus, ny is in the y direction, so the spin current is the same direction as the spin Hall current. Yeah, in this case, we obtain huge spin drive current, then more speed, H spin accumulation, then return back to the charge current. We have more charge current. This is why it's low energy state. However, if the direction of the spin current generated by spin split effect is different from the spin Hall effect, then there's less spin accumulation. Then you will have less charge current, longitude charge current. So then we can simply identify the near vector by the longitude measurement. Especially we know the spin split angle is much larger than spin Hall angle, which means we can obtain a really huge change in magnetic resistance with the flip of the near vector. Okay, yeah, then this is our conclusion. Then first we introduce our microscopic theory developed for the spin Hall magnet resistance, which can be applicable to any magnetic insulator. We find the microscopic mechanism of the spin missing conductance, also the spin sink conductance. Then we show our experimental demonstration of our theory in Ferromagnet GGG and the ferromagnetic insulator European sulfide. We find the ratio of the real and imaginary part of the spin missing conductance can be changed from much larger than 10 then to equal to 1 or less than 1. Then I also show our microscopic theory of the ferromagnetic resistance effect. We explain the Henle, Magno, and the anisotropic magnetic resistance microscopically. Finally, also apply to the automatic case. We obtain anti-fragment anisotropic magnetic resistance, also a linear term, linear to near vector term, which can be applied to identify the near vector. I think that's all. Thank you. Thank you for this.
Okay, thank you very much. So I have a very quick question. So how do you define the Snell vector in the? I mean, I should let others ask, but I was just curious about what is exactly the Snell vector in the altermagnet?
You mean the near vector?
Yes.
Near vector is the, you mean the here?
Yeah, you're talking about the Snell vector. I thought that Snell vectors are associated with anti-ferromagnet, not with altermagnets. So.
Yeah.
Oh, we always have this automatic because we always have this orientation.
Oh, okay.
Yeah.
I see.
So then you will generate.
So it's not the difference between the magnetization of two sublattices or anything like that.
Yeah, I think it's the difference. It's a difference between these two sublattices.
Oh, okay.
Yeah.
Yeah, sorry, I just wanted to ask that very quickly. So any further questions?
Yeah, okay, that last part is kind of not very clear to me, how you get that, but okay, all this.
Let me show you. I have prepared some slides. Maybe if the time is low, maybe I can quickly.
Yeah.
Oh yeah, I forgot that. Sorry, I forgot to send on my.
Yeah. And no,
There's some.
No, first, your altermagnets are of which type? D wave, P wave, G, I's. There is a full classification. So what is first? That is the first question. Because that would be very important. Then the effect should because you have certain.
Yeah, it's the common. It's the D. I think it's a D wave. Okay. Yeah. And I think I showed it. Let me do it here.
Okay, but if we can.
I see.
You can check the paper. No worry. Okay. Then if you have a D wave and then again the spin orbit coupling, because you have a spin Hall.
Yeah.
Plus
spin Hall plus
spin Hall plus spin split.
Spin split effect. Yeah.
So again, that theory requires it has some subtleties, because you have a spin orbit coupling.
Yeah.
Plus some altermagnetic order.
You
analyze it again independently, these two things.
Yeah. We try to set let's try to use solve it independently. So let me also, as you said here, will we include this here?
Yes.
Because before is the spin Hall effect include here. Now we know we have also spin current generated by the anisotropic spin split. So we add another term.
Okay, you do it at phenomenological.
Yeah, phenomenologically
Ah,
here. Here.
There is
In-
no microscopic theory of.
Yeah, here is not.
Okay, okay.
Because it's really hard to include all this. Yeah. So this is why.
Then I see it.
Yeah. So this is why I said all this theories is just a simple generation of our previous spin hole magnetization result. But it seems because this is it's really useful for experiment group, especially who are working in magnetoresistance. Yeah.
Yeah, I mean, first of all, you have to find an altermagnet.
Yeah.
With a spin-orbit coupling.
Yeah.
And
Exactly.
which is a conductor.
Yeah.
So name one. One material. I think there is no.
Right now,
You
even
never know what is going to be
because
happening in the future.
we propose some, but as you know, right now levels know it's really hard to
Fair enough. Thank you.
Making predictions is very difficult, especially of the future. Okay. Any further questions? Okay, I have a general question. So, in the first part of which is essentially connected to the work you did in the thesis, in your thesis, right? So, of course, I was not involved in that part, but so there is this decoherence time, right?
Yeah, exactly.
Caused by the magnetic impurities, right?
Yeah.
And I wonder if so in a sense, this magnetoresistance can be used to measure the decoherence time.
Exactly.
I see. Okay.
Yeah.
Because there was a lot of controversy. I was actually reviewing the literature recently, a number of years ago, about the decoherence caused by magnetic impurities, right?
Yeah, there's so many. Yeah.
And there were some papers by Glassman and by Van Delft and all these people. So I was wondering, of course, your microscopic calculation is not, I mean, I'm not sure. Yeah, maybe we can discuss about that.
Okay. Yeah.
Interesting.
I think we derive from the based on the open quantum system, so we can fully quantify the spin decoherence from this spin exchange. Yeah. So all this stuff also. This is
because I seem to remember that they said they had some results where they found some logarithmic dependence of this thing, like it's with the energy of the. Okay, we can discuss about that. It's kind of technical thing. Anyway, so I think it's maybe time to finish here. So let's thank Pong again. Thank you. Nice talk. Yeah. Okay. And he will be here for I think another week. So
next week we will still here.
Available. Okay. Thanks.
Thank you.
Thank you.
Thank you.